In addition to using rectangular coordinates to plot an ordered triple in three-dimensional space, we can also use what we call cylindrical coordinates, which is essentially the 3D version of polar coordinates that were used in 2D. If we take this ordered triple and project it down into the floor, in 2D we measure the value r to be the distance from our ordered pair back to the origin, and theta is measured from the positive x-axis over to that radial arm. And we'll use the exact same r value and theta value to come up to this ordered triple in 3D. The z-coordinate to complete this ordered triple is going to be the exact same z value that is used in rectangular coordinates. Now, because our r and theta are the same values that we used in two-dimensional space, we can use the same relationships between x, y, r, and theta when we convert from rectangular coordinates to cylindrical coordinates. And again, the z value from rectangular coordinates is going to be the same in both rectangular and in cylindrical. So what we'll see is that the triple integral over some solid 3D region in rectangular coordinates can be converted to a triple integral using cylindrical coordinates by substituting r cos theta and r sin theta in for x and y, and then we'll just use the same z value from rectangular with no substitution, and then we need to discuss what this dv quantity will turn into when we convert from rectangular into cylindrical. Let's consider the tiny volume of this polar cylinder. We'll call it delta V. The volume of any cylinder is going to be the area of the base multiplied through by the height, and the height of the cylinder in this case is a small change in z. The area of the base is going to be the same as this tiny area in the floor here, and we already know this from 2 dimensions to be r delta theta. So our delta V tiny volume is the area of that base times the height of our polar cylinder. And when we let the number of our approximating polar cylinders go to infinity, that's where we end up with dv, and we're going to use r dz dr d theta to represent that tiny volume in our triple integral. So when we convert a triple integral from rectangular form into cylindrical coordinates, we'll substitute r cos theta for any x value, r sin theta for any y value, and any z value will stay as z. And this dv quantity here, as we just saw, requires that we pick up a factor of r, and then we'll integrate dz dr d theta, or whatever order makes the most sense, given the shape of the 3D solid over which we're integrating.